in which we're going to start the chemistry's topic. Okay. But before that, let's start with the topic what we have studied in our previous class. So I'm just going to recapitulate the whole topic within 2 to 3 minutes, and then we will start with our brand new topic, that is imperfection in solid. Okay, so let's start. See, what we have studied till now in our solid state, we have discussed 4 to 5 lectures in which we have studied what actually a solid state is, what are the different type of solids. We have studied a table in which there are some unit cells, and we have studied that there is some packing efficiency which describe that yet the solids are perfectly arranged, but yes, there are some space, present in between them in the form of voids like octahedral and tetrahedral voids. So we have studied that packing efficiency wants to define us the actual percentage that how much our solid is completely packed other than the voids, other than the space. So this was the whole topic we have studied in our previous classes. So now let's start with our today's topic, that is imperfection in solids. What imperfection in solid wants to describe us, what actually imperfection in solids is. Let's start with that topic. Okay, so let's start. See class, whatever we have studied in our crystal lattice, how much they are completely arranged, how much they are completely ordered, yet there are some imperfection present in them. So I want to say that in solids, whenever we have complete package, whenever we have complete scenario with our complete packing efficiency, still there are some defects, still there are some imperfection in solid. So in today's topic is, whenever we are arranging our crystal lattice, there are some kind of error present in them, there are some kind of defects present in them, which is known as imperfection in solid. As the name clearly suggests, our solids are not completely perfect. There is some error, there is some kind of defect present in them. Okay, so let's start. The imperfection in solid is clearly defined as the defects that a solid consists whenever it aggregated small crystals. I'm repeating it again. I hope everything is okay. I'm repeating it again. Imperfection in solid is basically defined as the solid which, when arranged with aggregate small atoms or particles, they have some defects, they have some imperfection in them. Okay, so in this topic, we are going to study defects in our crystal lattice, defects in our solids, which are broadly of 2 types, point defect as well as line defect. Let me define what point defect and line defect wants to say you. See class, you know very well that whenever we have studied in our solid state, we have said that our unit cell have some crystal points. You know that very well. यही तो हमने स्टडी किया था कि हमारे जो यूनिट सेल्स होते हैं, they have some points in them, and these points are known as crystal points, lattice point, and these points are actually an atom, molecule, or ion. These are not only the point, these are the basically constituents of atoms, ions, or particles, in which are also known as point. So whenever we arrange our solid in the form of lattice, what happens? There can be an error due to a point, which is known as point defect. Or I would say the defect which arises due to only one atom or molecule or ion, that is known as point defect. In short, I would say point defect is defined as the imperfection or the defect in solid which is arised due to point present over there or due to atom present over there. Okay, same as it is if I'm talking about the line defect clearly suggests the name, the defect due to line. That means there is defect due to more than a number of atoms. That means there could be a defect due to a complete line. There are some atoms missing, there are some ions missing, due to which there arises a defect known as line defect. That means more than a number of atoms. Okay, but line defect is not in your syllabus, so we will not discuss that. We will just move with our topic, point defect. Okay, and point defect is the defect in solid which is only present due to atom present or molecule present in that particular solid. Okay, so let's start. Let's start with point defects and and its types. In point defects, the defect is only due to an atom, or we can say a crystal lattice. So it has basically three more types. Interstitial defect, valency defect, and the last one is stoichiometric defect. The stoichiometric and interstitial are almost same. So we have another type known as non-stoichiometric. So let me cut this. We have these three types. But in this topic, we just need to have a basic knowledge about these defects. The main important topic is the valency defect and its types known as Kothke defect and the Frankl defect, which are very important for your exam point of view, because we will given a differentiate that we have to differentiate the Kothke as well as the Frankl defect within 2 to 3 points. But let me have a just brief discussion. Let me have just a brief explanation about these defects. Let's start with the valency defect. The valency defect is defined as the defect arises when an atom or ion is missing from that particular site. I'm talking a compound which is sodium chloride. And in sodium chloride, if we're assuming that a particular atom has been missed, has been removed away from that particular crystal lattice site, that means the defect is known as valency defect, because the defect has been arised due to valency of that particular atom. Okay, we will further describe this defect with the help of Kothke as well as Frankl. But now that we have what stoichiometric and non-stoichiometric defect wants to define us. The stoichiometric defect and non-stoichiometric defect is based on a simple word known as stoichiometric. And stoichiometric means the interstitial site. Now you would ask to me, ma'am, what is interstitial site? Interstitial site means when you have atoms present and the space between them is known as interstitial site. It is kind of a cave. It is kind of, we can say Suraksha Chakkar. So basically, interstitial site is that particular site in which atoms and ions are arranged, and the space present between them is known as interstitial site. Now, the best point is our atoms or ions can easily locate over here. They can easily move to this interstitial site, and that's why we can say it stoichiometric defect. Okay, so let's start with our main topic, that is Kothke as well as Frankl defect. I'm gonna rub this, and now you will see how important and how easy are these defects. Let's start with Kothke defect. The Kothke defect is basically defined as the ion or solids which creates a vacancy whenever we remove remove a particular atom from its site. So we will say Kothke defect is basically a valency defect, which is due to valency of ions, or we can say missing of ions. So basically in Kothke defect, what happens, like we are having Na positive, Cl negative, Na positive, Cl negative, Cl negative, Cl negative, Na positive, Na positive, Cl negative, Na positive, and then Cl negative, Na positive, Cl negative, Na positive. I am saying that this defect arises due to ions. We have two different type of ions, a cation and anion. Cation is known as the ion with positive charge, and anion is known as the ion with negative charge. That you know very well, that you know already. I am saying that Kothke defect arises when the missing number of cations is equal to the missing number of anions. Let me repeat it again. The Kothke defect is defined as the vacancy defect, which is due to missing of ions. And in this defect, both are missing number of cations are equal to missing number of anions. Let we have a crystal site over here. We are having cation as well as anion, Na positive, Cl negative, Na positive, Cl negative. After that, Na positive, Cl negative, and then we must have Na positive. Okay, but this Na positive is not over there, it is missed, it is valence present over there, and same as it is, here must be present Cl negative, but this is also vacant. Since the number of cation missing is equal to number of anion missing, this is known as Kothke defect, and it decreases the density of substance, which is quite obvious. Whenever more than atoms have been missed, the Na positive have been missed, the Cl negative have been missed, that means the substance has lost its two ions. That means the density would be definitely decreased. The density would be lower down automatically. Why? Because it has lost its two ions, the mass would be decreased. That means the density would be decreased. So this is our Kothke defect. Would be lower. Density would be decreased. And the main reason behind this is that why do we have removed the same cation as well anion, that is to maintain electrical neutrality, to maintain electricity. What does that mean? कि हमें अपने सब्सटेंस को इलेक्ट्रिकली न्यूट्रल मेंटेन रखना है, हमें अपने सब्सटेंस को, अपने क्रिस्टल को इस तरह से मेंटेन करना है कि उसकी इलेक्ट्रिकल न्यूट्रलिटी would be always fixed. He should be always completely neutral. Suppose I'm saying that Na positive is missing, same as well as Cl negative is missing. You know very well that we have two types of ion, the cation as well as the anion, the positive charge as well as the negative charge. If I am saying the positive charge is missing, so to maintain it completely electrical neutral, इसकी neutrality को maintain रखने के लिए, to make it completely neutral, not even only positive, not even only negative, we are removing a Cl negative also. A Cl negative is also removed. Okay? And besides this, it has those two ions, so that means mass would be decreased and definitely the density would be lower down. Density would be decreased. Okay? This was all about our Kothke defect. And the examples over here are NaCl, KCl, silver chloride, silver bromide. These all are the examples which show the Kothke defect. Now we will move to our next topic, that is known as Frankl defect. I hope I have done the justice with this particular topic, what Kothke defect wants to explain us. Now let's move to our next topic, that is the Frankl defect. Okay. What Frankl defect wants to say to us? What is Frankl defect? Kothke defect and Frankl defect both are valency defect, but the difference is it is also with the ions. That means it is also due to in the ionic solids. But the reason behind this, that the smaller ions, suppose I'm having the cation, the smaller ions, suppose the cation is dislocated from its normal position and it goes to the interstitial site. Let me explain with the help of a diagram. We are having example of yes, silver chloride rather than sodium chloride. Let's say having example of silver chloride, or let me just take it as positive negative to just avoidance of any kind of problem. Same as it is, there must be positive, negative, positive, negative, negative, positive, negative, positive, positive, negative, positive, negative. Now I am saying that there must be a positive, but the Frankl defect says that suppose the cation is dislocated from its normal position and goes to interstitial site. I have just told you that interstitial site is a site covered by different ions. It's like a kind of suraksha chakra. It's a kind of a space present between the ions whenever they are arranged. Okay. So I'm saying that a smaller ion, suppose cation, that is dislocated from its normal site and it goes somewhere between the interstitial site. Okay, this is known as Frankl defect. Now you guys tell me, would it be affected over its density? Iski density par kya koi effect padega? And the answer definitely would be no. The density would be same. Why? Because the ions is still over there. The ion is just dislocated. That is just moved from one position to another position. But it is still present in that particular lattice. So since the size, the ions have not been changed, so the density would be same. Density would be same. For example, we are having silver chloride, zinc sulfide, and silver bromide. Now you have remembered that silver bromide I have put in both the examples, Kothke as well as Frankl. So this is an MCQ question that would come in your final exam, your board exam, very important, that which is an example of compound which shows both Frankl as well as Kothke defect. And the answer is silver bromide shows both Frankl and Kothke defect. All right. Is there left something? No, I have cleared all the topic. And since in Frankl defect, the ion is dislocated from its site, so Frankl defect is also known as dislocation effect. Okay, so you would get a question with 2 to 3 marks. Differentiate Frankl and Kothke defect. You can easily differentiate that in Frankl defect, density would be same. In Kothke, the density would be lower down. In Frankl defect, the number of cations are always equal. Only it is dislocated from one side to another side. Whereas in Kothke defect, the number of ions are missing. And the number of ions are missing must be equal to maintain electrical neutrality. And in this topic, is electrical neutrality changed? Not at all. The positive charge is still there, the negative charge is still there, it's just dislocated. Okay, So this is the basic difference between Frankl as well as Kothke defect. Very important for your MCQs as well as your for 2 to 3 marks question. Okay. So that was all about Kothke and Frankl defect. If you have any kind of doubt, we will discuss this in the last. Now, let's move to impurity defect, the topic with the impurity defect. I hope you guys have cleared the topic, the concept behind Kothke and the Frankl defect. Now, what is known as impurity defect? The impurity defect. Okay, as the name suggests, there is a kind of impurity present over there. Let me explain this a little bit. I am saying that if compound of sodium chloride and that particular solid is crystallized with, suppose, strontium chloride. Strontium is another compound which has also a positive charge. And I am saying whenever a solid sodium chloride is crystallized with another positive charge compound, suppose sodium chloride, what happens? Strontium here behaves like as an impurity. Our sodium chloride was firstly pure. Now strontium here behaves as impurity, and it displaces the sodium positive ion from it, and it itself goes into that position. So in short, we can say impurity is added to sodium chloride in the form of strontium. Now the question arises, strontium chloride, Cl2, that means strontium is of 2 positive charge. So I am saying the Na positive over here was displaced by strontium 2 positive. Now strontium is 2 positive charge. So what would we do? We would remove another sodium positive ion to just maintain electrical neutrality. Don't ever miss the topic that we have to keep the compound neutral. We can't make it positively charged or negatively charged. And strontium is 2 positive, so it has displaced 2 Na positive. And this is known as impurity defect. Okay. So this was very important, very easy topic. I hope you have got that whenever we mix our strontium 2 positive ion with sodium chloride, what would happen? It would displace 2 Na positive ion from that particular site, known as impurity. Okay. So now let's move to our next topic, that is known as Nonstop Geometric defect. Let's move. That is last topic, and then we would finish it within 5 minutes. And then we would have definitely a query session, and we will go to another topic in our next class. Within 3 classes, the solid state would also be over. So I hope till now you have made the all the notes, and you have prepared and revised all the notes. If you have any kind of doubt, you can ask me. Okay. So let's start with non-stoichiometric defect. Okay. Till now, what we have done, we have studied that the stoichiometry of crystalline substance was not disturbed. Okay. We have seen that either strontium 2 positive was fixed, it has replaced 2 Na positive, or the number of cations and anions have been mixed in equal form, or it has been displaced from one position to another. So I just want to say in that particular case, the stoichiometry has not been changed, has not been disturbed at all. But we have some solids, we have some examples, this is very rare, but yes, this happens, that stoichiometry is little bit disturbed, and which is known as non-stoichiometric defect. It is of 2 types, metal excess and metal vacant, or we can say metal deficient. Let's see about metal excess, and we will finish it within 2 to 3 minutes. What actually metal excess defect wants to say is, it has explained with the form of an example. It has said that, for example, we have taken an example of sodium chloride, and we have burning it in the form of sodium vapor. What would happen? The sodium positive from the sodium vapor would start depositing on sodium chloride. Let me repeat it again. I am having a sodium chloride and I'm going to burn it in the sodium chloride vapor. What would happen? From the sodium chloride vapor, the sodium positive would start depositing. And after some time, from this NaCl, the sodium positive on the same base would start removing, would start depositing to another substance. Okay, it would start to make another compound on the form of Na positive. So what would happen? The Na positive, whenever would be released, there would be left an electron behind it. जब भी हम बात कर रहे हैं कि Na पॉजिटिव जो है वो रिमूव हो रहा है, वो ऑटोमेटिकली is going to start depositing. What would happen? It would left behind an electron over it, and the electron behind left, that means there is excess of sodium positive over there rather than chloride ion, because to maintain neutrality, we can say the chloride ion has to be removed, has to be displaced by that particular electron. In that case, sodium positive is still there, but Cl negative is removed and fixed by only an electron. So Na positive would be in excess, and we would say this is our metal excess defect. Okay, this seems a little bit absurd, but this is the whole story, that whenever we are burning it in the form of sodium chloride vapor, after some time, what would happen? The Cl negative would be displaced by an electron, and there would be an electron, Na positive, Cl negative, Cl negative, Na positive, Cl negative, Na positive. So due to presence of this electron, we can say that the Na positive has been present over there in the form of excess. It has been present over there in extra form. And since the anionic site, the site of Cl negative, is occupied by an electron, this is known as F center, where F is a German word which means color. And this is a beautiful concept behind it, that whenever there is metal excess defect, our metal starts imparting color. For example, if I'm talking about NaCl, it starts releasing yellow color. Yes, it starts releasing yellow color. So there is a question which would come, that why do the solids start imparting color? Have metal deficient effect, which is not so much important, but we will just see that in that particular defect, we have seen that there is deficiency of metal rather than excess of defect. But I would say this F center, this color imparting, this is super important, which can come to your exam also. And just like I have taken the example of sodium chloride, I can take example of zinc oxide also. The zinc also start imparting color, and the reason behind this is metal excess defect. The zinc, what would zinc do? It would start releasing zinc 2 positive plus 2 electron. Okay, and this electron is capable, it is responsible only due to color present over there. Okay, this was all about metal excess defect as well as metal deficiency defect. So this was the whole topic in which we have studied the imperfection in solid, in which The main highlighting topic was the Kothke as well as the Frankl defect, as well as we have studied impurity defect with the help of strontium 2 positive, and lastly we have studied metal excess defect, which told us about the F center, that is the coloring partial. Okay, so this was the whole topic covered, the imperfection in solid. Next classes we will study the electrical and the magnetic property of the solids. Till now the topic has been